Well, now I am going to talk about abline and text. Suppose abline control 1. Although I have already talked about abline, see here we have taken another example. We are fitting abline means actually it is fitting up the line which has y is equal to abline means fitting of line y is equal to a plus bx, this line, and because there is one y intercept that is a and slope is b, so that's why it is known as abline, and its arguments are normal arguments are a b. A stands for the y intercept and b stands for the slope of the line. If we have these two things, we can plot a line. So here we have taken a real life example, that is we are fitting a regression model of trees data. Trees data we have already discussed. We want to predict volume on the basis of the measurement of girth. So the function LM stands for linear models. Actually linear model is the framework which is used to fit several kind of data like simple linear regression analysis, multiple linear regression analysis, analysis of designed experiments. For all these things, the basic structure, statistical structure is linear models, and that's why linear model, about linear model people say, statisticians say that it is the foundation of applied statistics. So here in R the function is LM. So LM, suppose we want to fit a line volume is equal to say beta 0 plus beta 1 into girth plus error. So we want to fit this model. Now what we can do, how we will write the first argument of the LM is the formula argument, and that is volume. Instead of equal to, we write tilde, volume and model as a function of tilde. Here neither beta naught is represented nor E, we just write the coefficient of beta 1 and that is girth. So this way this formula has been translated, and this structure of the formula is based on a paper of Winkelson and Rogers published in 1972 Royal Statistical Society Journal, and actually this has been made for writing formula in S plus, in R and some other packages also. So here this is the formula and this is the data is equal to trees. So if we run and if we print this, we are getting a brief summary of results. So this is the value of beta naught and this is the value of beta 1. This is the value of, this is the y intercept and this is the x intercept. If we have these two things, we can plot the line, and that is abline, and color is equal to red, abline. So first we will plot this and then control enter. We are plotting this, and then see if we write just M1, so that stands for M1 extracts these two coefficients. This is the y-intercept A and this is the B. So, both these are, since inside the M1 object they can be extracted, and just if we are typing abline M1, it will include the line, or other way abline, this is the A argument, this is the A argument minus 36.4 and the B argument is 5.0 and color is equal to red. Suppose we want to add one more line which is having the same intercept but slope somewhat increased, then it will be another line added and that will be blue. And then if we want to write the expression text, this is the first coordinate x means 12 from here, and y it is 70. So, it should be 12 from here and 70 from here. So, here this equation is to be written, and what is the text to be, the label is y hat is equal to minus 36 point something plus 5.6 into girth. So, this equation can be written like that. So, if we run, we get these things done. This is because of the text, and this is the original line, fitted line, and this line has been added with somewhat more sharper slope. It is abline, instead of 5.06 it is 6. So, it has different slope and it has been added. So, this way we can make use of abline and text. Some more examples of abline which I have taken from the manual of R. Plot C minus 2, 3. So, this is the on x axis minus 2 to 3, on y axis minus 1 to 5. So, these are the plotting regions. Type is equal to n, x lab is equal to x and y lab is equal to y, aspect ratio is 1. Then we are adding a line, abline h is equal to 0, h is equal to 0 and v is equal to 0, color is equal to gray 60. And then here h stands for, say for example, I would like to explain here itself. Suppose we want to add a line, vertical line at 12. So, the command is abline vertical line v is equal to 12. So, and color is equal to blue, and LWD line width is equal to 2. So, what it will add? It will add a vertical line at 12 here, and whose color is blue and width is twice to the normal. So, when we run this command, see here vertical line has been added. Similarly, if we want to add a horizontal line at 50, so what we have to do? Abline h is equal to, h stands for horizontal, say h is equal to 50, and suppose we want color is equal to say red, and LWD is equal to 1.5 times. So, when we will add this and we will run, we will get this result. This is the horizontal line with 1.5 times more thickness. This is the normal line. This is the 1.5 times more thicker than 1 point normal, and this one is the 2 times thicker than the normal, and color is blue. So this way we can add abline h is equal to, and similarly we can do some other operations. So those operations are made here inside the commands. See, plot c minus 2 and x lab, y lab, and then abline h is equal to 0, v is equal to 0, color is equal to gray 60, text 1 0. So that means on x axis it is 1, from y axis it is 0, abline h is equal to 0, abline h is equal to 0, color is equal to gray 60, and ADJ adjustment is 0 0.2. Similarly, abline a is equal to 1, abline a is equal to 1, b is equal to 2, and color is equal to 2. Then text at 1 3, from x axis it is 1 and y axis it is 3. So here on x axis it is 1 and from y axis it is 3. So it will come somewhere here. So color is equal to 2, adjustment is this one. So if we will run, we will get this result. This is abline, this is abline, color is equal to 2, this is the abline, color is equal to 2, red, and this is abline h is equal to 0 at 0, h line, abline is equal to 0, color is equal to gray, color is equal to gray. If we will change the color, instead of using gray is equal to 60, suppose we change gray is equal to 10. See what will be the effect. No, instead of gray, suppose we are changing this to blue. See what will be the effect. It has changed to blue. It has changed to blue. It has changed to blue. And here color is light gray. So this way we can make changes in these things. Drawing a polygon. Drawing a polygon, actually polygon, you know, the simplest example of polygon is like triangle or rectangle or hexagon. They are the examples of polygon. Here I am giving a simple example of polygon. Plot 1:20, on x-axis 1:20, on y-axis 1:20, plotting character 1:20, and then to draw a polygon, we are giving the coordinate x is equal to 2 4 6 and y is equal to 4 4 15, and then we are adding this polygon x comma y, LWD is equal to 2, color is equal to red. So see what is the effect. This is the plotting character. Then we are running A, we are running Y, and then we are adding a polygon. So it needs to be run in one go. See, this is the polygon. This is the polygon whose coordinates are x like 2 4, 4 4, and then 6 15. 2 4 4 4 and then 6 15. So these are the 6 15. So these are the coordinates which are filled. So this way we can add a polygon. to a figure. Just we have to specify the coordinates. Now, a more advanced example of polygon. Here it is a kind of data simulation from random walk. It is a kind of data simulation from random walk. So, n is equal to 100, x is equal to c, it is 0 to n, 0 to 100 and then 100 to 0, and this has been organized in 1. Then y is equal to c, 0 to cumulative sum of these values, of these simulated values, and then reverse of these cum sum, this c 0 sum. And then we are plotting x, y, and then type is equal to n, x lab is equal to time, and y lab is equal to distance. Then we are adding a polygon x, y, and then curl is equal to gray and border is equal to red. Then we are going to have title of the figure, distance between Brownian motion. Distance between Brownian motion. So, we can have control enter, this is n, then we are simulating 1, 2. If we will print this x, what kind of data has been generated? 0 to 100 and then 100 to 0. So, this is the data x, and then y, cum sum of random observations. Say for example, if we are talking of x is equal to say r nor say 10, then we can print this x is like this, then cumulative sum of x. See what it is doing? It is doing cumulative sum. Say 0.5 plus 0.5 plus 0.7, so it is this one, plus 0.7 plus this, it is this, then this plus this. So, this way it is cumulative sum. So, this is the cum sum function. Then plot x, y, type is equal to n, x lab is equal to time, y lab is equal to distance. So, here it plots. This is just, type is equal to n means it just fix the coordinates and no points. And then we are going to add a polygon x, from x-axis it is x, from y-axis it is y, and color is equal to gray and border is equal to red. So, now we have to run the whole chunk. See, this is the Brownian motion, distance between Brownian motion. So, this is the plot which has been created by polygon, and this title of the figure. Now, I am going to talk about segments, line segments. Say x is equal to 1:20 and y is equal to 20 into 1, plot xy, then segments x is equal to x0 is equal to 4, y0 is equal to 10. So, this will be the beginning point, and x1 is equal to 10, y1 is equal to 20, this will be the end point, and this segment will be added. And similarly, to put an arrow x0 is equal to, this is the beginning point, x0 5 and then y0 8 and then x is equal to x1 is equal to 8 and y1 is equal to 18. So, this way it will add. See, we can print x. This is the data had been generated x, then y, it is xy, no, it is y only, y. So, we can look into, control y. So, 2y, y22 1. So, it is just reverse of this. And then we are plotting this. And these are the plots. X is equal to 1:20 and y is equal to 1:20, and these are the plots. Now, we want to add a segment from x is equal to 0 to x is equal to 0, 0 and y0 is equal to 10. So, y0 is equal to 10. So, here from here to x1 is equal to 10, and y1 is equal to 20. So, somewhere here. So, if we run these commands, we will have this picture. So, this is the arrow and this is the line segment which is being added here. Now, some more advanced, a more complex example. Here what we are doing, RUnif stands for random observations from uniform distribution, uniform 0 1. So, 12 random observations are taken from uniform 0 1, and here 12 random observations from taken from normal 0 1. L is equal to order of x and y, x is equal to x1, y is equal to yi, and then plot xy, main is equal to arrows and segment, and then we are generating a sequence, and then we are adding s is equal to minus length segments xx, y s plus 2 like this. So, we can generate the plot of these commands just. So, these are the outputs, of these commands. An example of bar plot with SD. This is also an example of points and t-apply. Here we are already having a data insect sprays. These are the names count and insect sprays. This data set is there. So, these are the head insect sprays, So there are two columns, counts and insect sprays, and there are 6 sprays. So this is the insect, and then we are going to use tapply. Tapply is a function like apply. Apply works on the matrices or on arrays, whereas tapply works on a vector. Like here in tapply, the first argument is numeric vector, which is count, taken from this data, count, and then we have selected another indexing variable, and that is the factor vector, and this one AABB, and then we have computed mean of each group. So it works on each group on, say for example, what is the mean of AA, then BB, what is the mean of C, what is the mean of these D observations, what is the mean of this E observation. So for these things we use the function tapply. So tapply, and if we print this, control plus enter, it prints means, mean of A, mean count of A, mean count of B, mean count of C, mean count of D, and mean count of E, and mean count of F. So these are the mean counts of all these sprays. Then if we want to compute SD of each group, say for example we have computed mean of this group, now we want SD of this group. So what we have to do, here again insect sprays, count, numeric variable, then indexing variable, spray, and then SD is the function which we want. So control S and control 2, this M is the mean, where S is the SDs of these variables. So if we want to bind them, column wise binding, on the first column it is mean and on the second column it is SD. So we have to use C bind, C. M, mean of A is 14.5, mean of B is 15. Similarly, SD of A is 4.7, SD of B is 4.2, like this. And suppose we want error bar plot, the height should show the mean at each level of A or B or C, and then a vertical bar on above, it should show strength. This is known as error bar plot. So here what we have to do, the command is BP is equal to bar plot. We are assigning, instead of just getting the figure, we are assigning this to an object. So bar plot M is the mean. Then Y lab is equal to average count, X lab, spray type, and Y limb is equal to 0 to 25. And then arrows BP, the first point is BP, second point is mean. So the beginning point is BP and mean. Then end point is BP, that is the height, and then the upper point is M plus S, mean plus standard deviation, and angle is equal to 90 and length is equal to this. So see, this is the bar plot, this is the error bar plot. So these are the SDs and these are the means, and these are the SDs. So this kind of graphs are often required by the biologist. And here, due to angle 90, it is 90 degree, and this length is equal to 0.1, it shows this length. If we will not show this length, see what happens. length length, length is equal to 0.1. Yes. So if we make the angle, say for example 60, see what happens. So this angle is 60, otherwise 90. If we make it 90, it will look like this. It will look like this. So this is the angle. This angle is controlled by here 90. Now 90 degree. 90 degree from here. So this is all about 2 days, and tomorrow we shall talk about some other aspects of data analysis using R.